Hello everyone, and welcome to my channel. Today, we will understand resource management in Kubernetes. This is our agenda for this video. First, we will understand why we need resource management in Kubernetes. After that, we will discuss the units used by Kubernetes, and last but not least, we will discuss how we can manage our resources, within which we will also talk about the different quality of service classes and how Kubernetes assigns pods in those different priority classes. So, let's first understand why we need resource management. As you can see, we have a control plane and two worker nodes, 1 and 2. Within the control plane, we have two components, Kube API and Scheduler. Now, for instance, let's assume that an admin wants to deploy a pod on one of these nodes. So what happens is that the request will first go to the Kube API through a command from the admin, and then the Kube API will forward it to the scheduler. From here onwards, the scheduler will decide where to place or run the pod, either on node 2 or node 1. If we see things from the scheduler's point of view. So here is the problem. How would the scheduler know what are the requirements of the pod so that it can accommodate the pod in one of the nodes? And which one of the nodes in the cluster has enough resources to run the pod? These questions are only possible to answer if the scheduler knows how many resources the pod will need to run. In order to schedule pods effectively, the scheduler has to know the minimum and maximum allowable resource requirements for each pod. A pod that requires 1 GB of memory cannot be scheduled on a node with only 100 MB of free memory. That's where Kubernetes resource requests and limits come in, which we will discuss in a bit. That is where we need resource management in Kubernetes. For now, Kubernetes understands how to manage two resources, CPU and memory. There are other important types of resources, too, such as network bandwidth, disk I/O operations, and disk space, and these may cause contention in the cluster, but Kubernetes doesn't yet have a way to describe pods requirements for these. Now, let's discuss the resource units that Kubernetes uses. CPU usage for pods is expressed, as you might expect, in units of CPUs. One Kubernetes CPU unit is equivalent to one physical CPU, which is our personal computer or laptop, which we use daily. On the other hand, if you are using one of the public cloud providers to run your application, it is equal to one virtual CPU of AWS or one Google Cloud Core, or one vCore in Azure. So you have to use these units depending on your environment. As I said, resources managed by Kubernetes are CPU and memory or RAM, but most pods don't need a whole CPU, just a portion of it that we need. So Kubernetes gives us the capability to use a part of the CPU or memory, and they are represented or expressed in milli-CPUs, sometimes called milli-cores. Same for memory, which is measured in bytes or megabytes. We discussed why we need resource management and its units to represent them. Now, we will be talking about these concepts, resource request, limits, and quality of service. Let's start. The first one is resource requests, which is the minimum amount of that resource that the pod needs to run. For example, in the template you can see that a resource request is defined with 250 milli-CPUs and 10 MB of memory means that the pod cannot be scheduled on a node with less than those resources available. If there isn't any node with enough capacity available, the pod will remain in a pending state until there is. Then there is resource limit. In Kubernetes, a resource limit defines the maximum amount of CPU or memory that a pod is permitted to utilize. When a pod attempts to exceed its allocated CPU limit, Kubernetes enforces throttling to control resource usage and preserve system performance. However, the consequences differ when a pod surpasses its memory limit. Kubernetes takes a more stringent approach by terminating pods that exceed their memory limits. If a terminated pod can be rescheduled, Kubernetes will attempt to restart it, typically on the same node. Certain applications, like network servers, may exhibit increasing resource demands in response to growing usage. By setting resource limits, Kubernetes ensures that these resource-intensive pods do not monopolize cluster capacity, maintaining fairness and stability. Based on the requests and limits of a pod, Kubernetes will classify it as one of the following quality of service classes: guaranteed, burstable, or best effort. Let us see one of these one by one. So the first is guaranteed class. So, to understand this, let's say that we have a control plane and a node, and within the node, a pod is deployed with the specification as shown. As you can see, the request and limit are equal. When requests match limits, a pod is classified in the guaranteed class, meaning it is considered by the control plane to be among the most important pods to schedule, with a high priority, and it will do its best to ensure the pod is only killed if it exceeds the specified limits. For highly critical production workloads, you may want to consider setting your limits and requests to match in order to prioritize scheduling these pods. The next is Burstable Class. As you can see that we have the same setting, but the request and limits of the pod are different. Request is less than the limits, which gives it the reason to burst out or, in other words, to go beyond the request up to its limits. When there is a difference between the request and limits, the control plane classifies them as burstable pods and gives them a lower priority than guaranteed pods. Kubernetes will allow them to burst above their request up to their limit if capacity on the node is available. If the pod is using more resources than requested, the pod may be killed if the control plane needs to make way for scheduling a pod of a higher QoS class. The last one is the best effort and easy to understand. If a pod does not specify any requests or limits, it is considered to be best effort, which is the lowest priority. Pods are allowed to use whatever CPU and memory is available on the node, but it would be the first to be killed when the cluster needs to make room for higher QoS pods. Thank you for joining me today in exploring Kubernetes resource management. If you found this video helpful, don't forget to like, subscribe, and share for more content on Kubernetes and cloud-native technologies. Until next time, happy learning and happy Kuberneting. Goodbye.